My name is actually quite long, as sometimes it's difficult for people to pronounce it very right. But just call me Amobichukwu Amanambu. That's my name. I had my first degree at University of Ibadan back in Nigeria, and also my second degree in geography in the same university. And I also had a second master's degree in United Kingdom, Loughborough University. I also went to China. I spent 2 years for a research. And then from there, I came to the US, do my PhD, and I'm here. My research actually focuses on impact of human activities or anthropogenic activities and climate change on hydrological systems. And hydrological systems could be groundwater, surface water. But today, I'm focusing on surface water with emphasis on rivers. The topic today is on river deformation, how it actually affects floodplain inundation and hydrological drought. This work, and I want to say thank you to AWI for inviting me to come and make this presentation. But this work was actually sponsored by the EPA. It was a 5-year project. And right now, we have already published 8 peer-reviewed papers, and 2 are under review, and 2 are actually under preparation. But we concluded the work last year, but I decided to just make this a presentation. It's a lot of work, but I'll try to compress all of them in a 45-minute talk. When we say river deformation, what are we talking about? We are making reference to either aggradation, that is the addition of sediments on a riverbed, or degradation, removal of sediment in that riverbed. So the idea is, how does these 2 processes, aggradation and degradation, actually cause flood inundation changes and also hydrological droughts? As we all know, the river landscape has been greatly impacted by both natural phenomena. You can say precipitation in amount and also in intensity, and also by anthropogenic influences. You can actually say a dam, which is a great example. And when a fluvial geomorphologist or hydrologist think of the impact of dam on any river, the first thing they think about is incision, that is deepening of the river channel. Yes, Leopold sometimes back in his article talked about a hungry water. And when he make reference to a hungry water, he was talking about when you place a dam along a river course, what happens is that it keeps the sediments away and makes the water hungry. And along the river course, this hungry water begins to wash off those sediments. That is what degradation is about. And of course, dam construction does not only cause degradation, also reduces water level as a result of the deepening of the channel close to the dam. And of course, when we talk about reduction of water level, you make reference to hydrological drought. When we say hydrological drought, we are talking about reduction in water level. And of course, hydrological drought has been exacerbated by human or anthropogenic alterations. Not just only dam, dredging, dikes, and other anthropogenic structures have had great impact on rivers around the world, disturbing sediment and also changing the geometry of the river platform. In this research, I'll just jump into what the questions are. Now, does changes in riverbed have implications on floodplain inundation? That's a great question. The second question, what are the critical factors that drive riverbed deformation? What are those factors that actually drive this aggradation and degradation? Does stage, when we say stage, we are talking about water level. Does stage matter for hydrological drought assessment? We are going to look at all these questions and also ask a question of what is more after all these 3 questions. The study location for this research was actually in Apalachicola River. Excuse me. The Apalachicola River is located in the Apalachicola-Chattahoochee-Flint River Basin. And this basin drains an area of 51,000 square kilometers. And the Apalachicola River is an important area of biodiversity hotspot within the southeast United States. And a dam is there, constructed. The Jim Woodruff Dam, if you can look at the dam, the Jim Woodruff Dam. And also an artificial lake was also created after the dam was constructed, which is Lake Seminole. Interestingly, this area is actually an area of important legal battle. By the time you go online and search tri-state water wars, the first thing you will see is about the ACF basin. Georgia, Florida, and Alabama, we are battling it out as regards to the water resources within this area. Georgia need water for the growing Atlanta city. Florida in itself is interested in its fish industry, while Alabama is, agriculture and also hydroelectricity. Alabama and Florida sued Georgia. Oh, you're using all these resources. It is affecting the ecosystem. Of course, Georgia won. Why? Because Florida and Alabama do not have scientific evidence to prove that the water being taken from Georgia is actually impacting the ecosystem. As scientists, we know it does impact. But of course, I mean, when I was in Florida, I was sad. Oh my God. I'm indebted to Florida in a way, saying, why will Florida lose? Now I'm in Alabama. Actually, both Alabama and Florida actually lost the case. So I was in a conference some times back. Pragba is not here when he was presenting, and he was asking a question. Who makes this kind of decision? Is it Supreme Court or scientists? I think it's a question that is left for us to answer. If it is the Supreme Court that decide the action to take with regards to water conservation. The research area is actually focused on across River Mile 75 and 105, just the upper part of the stream. And within the entirety of the river channel, over 100 wing dikes were constructed. So not just only the dam, but you can see these red marks here represent the wing dikes being constructed across the stretch of the river. Not just only these anthropogenic structures, over time, the freshwater mussels has been declining as a result of several anthropogenic interventions performed within the river stream. Of course, the river feeds into the Gulf of Mexico, and the dam started construction in 1954, but was opened in 1957. And not just only dam and dikes, dredging started as far back as the 1800s, during the early time of navigation, even during the Civil War in the United States. And early dredging started around that 1870s, but heavy dredging, disposing of those dredged materials, and also artificial cutoffs actually started around the 1950s. But there was a Restore the Apalachicola River Ecosystem Act that was enacted 2002 so that the river will be able to take some breath and start recovery from all the several impacts. So the passive recovery started from 2002. But it still doesn't mean that the impact of all these activities are still not felt. So today I want to bring out to everyone's face to see how much of the changes has actually occurred within this river. So the first paper I'll present is Drivers of Riverbed Modification, Impact on Depth and Inundation. So what is the gap? When we talk about the gap within this idea, I'm talking about implication on riverbed geometric changes. So several literature, I just put one, has looked at degradation, aggradation, and how they have impacted geometric characteristics. But this kind of research actually focus on within the channel and not looking at the floodplain and other part of the ecosystem. The focus has always been within the channel changes. And also in the literature, others actually itemized drivers that create this deformation. It could be flow, it could be water surface elevation, also dredging, dam construction, including natural phenomenon and also anthropogenic activities or structures. So the question now arises as a knowledge gap. What are the most important driver of riverbed deformation? Question, what is the most important? Can machine learning identify this driver? Is it possible? So how does this deformation impact inundation? All these questions are actually not really well developed within the literature. So it's part of adding into the growing literature. So first objective is to evaluate the amount of aggradation and degradation within the channel, across the entire reach, using depth of difference. When I say depth of difference, you are looking at taking two digital elevation model of two different time periods and subtracting them to get the difference. Then sediment volume was also determined. So the second objective was to identify most important factors that drive the deformation using a machine learning model, which is random forest. So the third one is to evaluate the depth and floodplain inundation changes between the pre-dam and post-dam periods, also using relative water elevation model, geometric properties, and also HEC-RAS hydrological model to actually look at how floodplain inundation extent has changed over time. So data sources include hydrographic survey from 1960 and 2010 from the Corps of Engineer, and also LiDAR point cloud that ranges from 0.5 to around 1.2 points per meter squared, and also hydrological data discharge and stage was used, and also land use, land cover. Now, when we look at the flow chart, a very simple flow, though it might look complicated, but the first step, which is number one in orange. So what I did was to merge the LiDAR point cloud collected and the hydrographic survey to create digital elevation model through triangular irregular network. I'm going to explain that in a bit. Imagine having hundreds and hundreds of hydrographic survey sheets given to you. And each transect, you have to digitize each transect across 180 kilometers of a river. You see how tedious that work is. I will say thanks to the undergraduates who did most of the work. They are not here today. Of course, QA/QC was done. So after digitizing this, when you look at this, the Corps performed a survey in a meandering channel. You cannot just take this data, perform interpolation, and get your rasters or digital elevation model. Because if you do that, those interpolation, the backbone of interpolation actually depends on Euclidean distance. It assumes that point A and point B are actually a straight line, which is not the case in a meandering channel. So the first thing that we did was to use a technique called forward and inverse transformation. The idea is transforming the hydrographic survey data from Cartesian coordinate system into channel-centered orthogonal coordinate system. The idea is to ensure that we register the perfect distance between point A and point B. And having done that, the next thing we did was to convert these transformed data into raster surfaces using ordinary kriging method. Then extracted the points, then transformed the point back to its original coordinate system. So after this, then we transformed the data into a digital elevation model through the triangulated irregular network. So this is the triangular irregular network. This method, or the digital elevation model you download from USGS. This is the method that USGS uses to create the digital elevation model. And of course, from triangular irregular network, we're able to create raster surfaces, which is digital elevation model for the riverbed. The next thing that we did is to create cross-sections, over 300 cross-sections, then started calculating the geometric characterization of the 1960 digital elevation model and that of the 2010 digital elevation model. The bank full level, channel width, area, all the geometric properties that we're able to perform. We did them to be able to compare the changes within those two channels. After that, the next thing, to perform inundation extent, we took the digital elevation model, then inserted it into HEC-RAS model, added our river data, stage data, roughness coefficient, the land use, land cover, and also to be able to create inundation extent. So the next step was to take that same digital elevation model. We want to look at what are the drivers and how do we get a difference in elevation between 1960 and 2010. And the simplest way we're able to do it is to first get the digital elevation model, perform some uncertainty analysis to be sure that digital elevation model that we developed using the process I've described earlier is actually very good. Then having done that, we divided the elevation into different sub-breaches. Each sub-breach has a length of 1.6 kilometers. Then, taking each sub-breach to generate the depth of difference, which is DOD, we subtracted the 1960 digital elevation model from the 2010 digital elevation model. Now, to calculate the sediment volume, so we multiplied the DOD by the surface area of the digital elevation model to actually know what is the volume of the sediment that either deposited or was actually removed within the riverbed. Of course, we were able to go through the literature and itemize drivers that are very important in causing river deformation. These variables we actually got either from the literature or availability of data. So we use entrenchment ratio, floodplain width, flow velocity, dikes, dredging. So it's a mix of natural phenomena and also some anthropogenic structures within the river channel. So all the variables, including the DOD, were fed into a random forest regressor and predicted a DOD to see what variable play a key role in actually not causing, but can be used to best explain the changes or deformation within the channel. So here is what is going on. So you can see from upstream, which is river mile 106 up to river mile 75 downstream, you see that the total sediment gain has actually been increasing downstream of the channel. But when you also look at the total sediment loss, you will see closer to the dam, the sediment is actually reducing. I mean, you can easily explain this. This is degradation. You can easily explain it based on what I've said earlier, the hungry water that is ready to wash off any sediment it sees along its course. You can easily see how much of the sediment is lost closer to the dam as compared to the far away. So when you look at the extreme end, you will see suddenly there is a peak in sediment. Interestingly, from the 1960s to 2002, the Corps actually dredged sediment of about 1.7 million cubic meter within that area and actually dredged and dumped it by the floodplain. So what happens is that when rain falls, or those sediment goes back into the main channel. So they have not actually done anything. So at the end of the day, you have even more sediment within the main channel. And the total sediment that was lost is about 6.5. And it's not up to what is happening in Mississippi, where there's hundreds and hundreds of millions of sediment being lost to the ocean. Now, when you look at what is going on there, you see that the dredging volume was actually highest closer to the downstream of the dam, just as we have seen how high it is. So this amount of dredging material, and this is where this dredge material were actually deposited. So dredging volume and dredging disposal. So you can see at the end of the day, the amount of, you took some sediment away because you wanted to create a more deeper channel, place it on the floodplain. At the end of the day, this sediment still finds its way back into the channel. For the random forest, so we tried to look at using the Higgs-Beam plot to see how good the model actually performed. So when you look at the red dots, you see most of the points were concentrated at the red and actually at the yellow dots, and fewer were at the blue, signifying that the model actually performed well for both low flow and actually high flow predictions. And also for evaluation, you see most of the evaluation metrics actually show very low value, signifying that the model performed very well. So let us look at the relative importance. So you see the dam plays important role. The dam is actually highest with regards to what the random forest is saying, signifying that the dam play more important role. This is not to say the machine learning model is not saying that dam is responsible. It's saying that dam is the most important variable that you can use to explain the deformation, what is actually going on. When I was creating this research, I postulated that, because I read a lot of literature within the area, I postulated that, dam is number one and dredging is number two most important anthropogenic factor. But when I got the result, I was very shocked to see that dikes is actually number two with regards to causing deformation within the channel. So let us see why dike is actually second most important. So when you look at this DOD here, let's pay attention to this DOD, which is the last one. You see that the orange area where the dikes are located So what do dikes do? So actually the initial thought of the Corps of Engineers is to put those dikes so that they will move the water into the middle of the channel and create more depth for easy navigation. But what happens is that those dikes are accumulating sediments. So they create more aggradation in some part of the river channel, okay, and also increases velocity within the channel and creates more depth. So another thing again you should look at is this. Opposite most of the places where the dikes are accumulating more sediment, the river is actually deepening. So you can see this color brown here. So you look at them, you see opposite where the dike is accumulating sediment. That means as the dike is accumulating sediment, it's pushing the water away from it, opposite it, and the river keep causing what? Incision, creating what? Both aggradation and degradation within the channel. So that is why dike played a key role in explaining, the deformation within the channel. So also look at the tower elevation from river mile 106 up to 80. You see degradation is more closer to the channel and slight degradation, although closer to the dam. But of course, degradation and aggradation can vary when you move away from the dam. And you see there's a deep pool. We found a deep pool at river mile 92 to 95, and we are shocked as to why is this here. So we decided to go back to the falls. We rented a boat. We took a sonar to go to this river mile, and we actually found that there is actually a deep pool. And so we begin to ask, why could there be a deep pool? And by the time we looked at the geology of the entirety of the river, the geology of the river is actually limestone in nature. And we concluded that these deep pools could be possible development of sinkholes as a result of what? The presence of the limestone, which can easily just cave in. We are not sure of, this is just a possibility, what we are postulating, and because those sinkholes are there, suddenly they appeared. Given the geology of that area, this is a possibility. Also, when you looking at the geometric properties, you will see that there are changes comparing the 1960 and the 2010. So you see how the river has actually changed. When I picked a cross-section from river mile 89.8, you see that the area changed, the depth changed. So even the depth, the mean depth has actually increased compared to 1960. So when you also look at the channel area, increase close to the channel, close to the dam, the channel area, because of what? Incision, degradation. The closer the cross-section is to the dam, the more depth is being created as a result of what? The dam causing incision. Of course, when you look at the channel width didn't really change so much closer to the channel, because closer to the dam, because the dam is not causing lateral erosion, but it's causing vertical erosion and not necessarily affecting the side of the floodplain. Instead of it going this way, it's actually going vertically. So closer to the dam, there is no a lot of changes. And of course, the mean depth, closer it is to the dam, the deeper the channel, and also changes in width-depth ratio. So when you look through all the geometric properties, you see that there is a significant change across between those two periods. Just few instances didn't show that there is a significant difference, but indeed most of the geometric properties are showing significant difference between those two periods when we look at it upper, middle, and lower course of the channel. Changes in inundation. So when you look at, this is just a short video that I created when I was developing the flood inundation model in HEC-RAS. So when you look at this video, you realize that over time, the inundation on floodplain is actually reducing. It's a gradually reducing. Both in seasons, even to the more recent time, water is less inundated on the floodplain, simply because when the channel is incised more, less water flows into the floodplain because water elevation is not as high as they used to be. So I'll just give us a time to just look at it and see. You can see towards close to us, inundation is reducing on the floodplain. Also, this is another graph to also depict what is going on. So you can see that inundation has actually changed when you look at similar flows across those two periods. So at flow of a bit above 500 cubic meter per second, you see that inundation has actually changed on the floodplain. Even the same on a higher flow, inundation has actually changed. When you look at the floodplain, you see that in some cases, there are no inundation in them. Even at very, very high flow, at 1500 still inundation on the floodplain has actually reduced. This is just simply attributed to the amount of or changes in both aggradation and degradation, especially degradation, as a result of the fact that when the channel is incised, less water, okay, is inundated on the floodplain because water level has reduced. Not just only floodplain inundation, also the depth, but we'll talk about that in another research. But here, when you pay attention to this, you see inundation with regards to percentage to floodplain. So the amount of inundation regarding how much it has inundated on that floodplain. For the pre-dam period, you see that for the pre-dam period, we have more inundation on the floodplain as opposed to the 20 post-dam period. Okay, so more inundation as opposed to the post-dam period. And in some cases, the inundation difference reached about 30% with regards to differences in inundation. So what is the take-home message? That dams have great impact on river geometry and floodplain inundation characteristics through time. In some cases, there are differences of up to 30% for floodplain inundation, and degradation of the channel is highest closer to the dam, and as it varies downstream, and also aggradation also vary with degradation. And dikes was found to be second most important anthropogenic structure that actually affect or cause degradation and aggradation within the channel. So the RF model shows that dam is most important factor that cause the degradation and also part of the aggradation within the channel. So what is the next paper? Stage matters for assessing hydrological drought and disconnectivity. Stage matters for assessing hydrological drought and disconnectivity. When we talk about hydrological drought, we make reference to lowering of water level within rivers, lakes, groundwater, and streams. That is what hydrological drought is, but it has implication on river connectivity. And if you read through the literature, when different scientists are defining hydrological drought or analyzing hydrological drought, they often say as a result of low rainfall or lack of it. That is what, but the question still arises that what happens to human-induced low flow conditions? They are also hydrological drought. But the definition does not capture human impact or maintenance decision with regards to what is happening in our streams. So, and this implication cut across with regards to water quality, temperature, fragmentation, floodplain disconnectivity. So the question is, do we need to include management decision when we are defining hydrological drought? When we are also talking about hydrological drought, how then do we include stage height or this management decision? And one of those ways is actually to include water level when assessing hydrological drought. The reason is this: of course, we all know that discharge captures all the characteristics of, including the flow regime, sometimes even the structure of river platform. But what water level or stage does is that in every location, it shows more insight into the changing structure of that river, far better than discharge. So it is not to say that when you are talking about hydrological drought, you should throw discharge away. No. But when you are assessing hydrological drought, especially in those rivers that have been heavily influenced by anthropogenic disturbances, stage is a critical variable that you should include, because stage in itself shows what those differences in structures or changes within that channel. So also in doing this, we also have to think of concept of eco-deficit and eco-surplus. So in hydroecology, this concept highlights change in stream flow regime when you are using flow duration curves, especially before and after a great event. So this concept can actually define and explain what is actually going on within the river when you compare using discharge data and also stage level data. So a look into the literature. I dived into the literature to look at over the years, what is the interest of researchers with regards to hydrological drought? You can see it has been increasing and really peaked in mid-2000. Extreme peak in they were just, flat all of a sudden because, of course, you can easily say it's because as a result of climate change. But when I also go deep down into the literature to see what are the variables that these researchers actually use when they are, of course, they talk about climate change, anthropogenic climate change, and so many things happening within the river channel. The papers, 1,095 papers was actually looked at, and within all these papers, only 6.7% considered water level when they are analyzing hydrological drought. Despite, I was talking to my student a few days ago, and I was telling, we were looking at hydrograph, and I was telling them that, show me a river that has not been influenced by anthropogenic structure, and I will tell you where the problem is from. Almost all the rivers in the world today, you cannot find a completely rural river that is undisturbed. So almost all the rivers are disturbed. So when you are looking at hydrological drought, you should think of water level, because water level can add value, can add more explanation when you're looking at what is actually going on within that river. Of course, literature gap, limited quantification of hydrological drought using stage height, which I've already talked about. So insufficient studies on impact of low flow conditions in floodplain connectivity. So these are the literature gap that were itemized that actually propelled the reasoning for this research. So the first thing we did was to analyze changes in drought characteristics between pre-dam and post-dam periods, and also developed a relative elevation model, which you can also call relative surface water model, okay, that uses water levels connected to low flow conditions as an indicator of river disconnectivity. So the relative elevation model is connected to water level.
Quick question, would you mind explaining, defining hydrological drought in this context?
Okay,
and
okay.
Why you're focusing on that?
Okay, so when hydrological drought, as I said, is actually the lowering of water level within a river channel. And most of the time, when you read through the literature, they often say because of lack of rainfall or reduced rainfall. But in this instance, we are looking at hydrological drought with regards to human-induced low flow. That means low flows that are caused by human activities. I've explained earlier, dams can cause low flow, dredging. All those human activities reduce the amount of water that flow in a river. Okay, so in this instance, instead of just saying hydrological drought is a lowering of water level in a river as a result of rainfall. So you can also, as a result of lack of rainfall, you can also say as a result of management decision. Okay, in other words, it means that low flow can be resulted as a result of management decision, human impact, and what have you. So we developed relative elevation model. So relative elevation model, I'll say explain what that is. So it uses water levels connected to low flow tech threshold as an indicator of river disconnectivity. So the first thing to do was to try to look at the data and see the trend. So we use Mankenda just to look at what the trend is saying, if there's a reducing trend with regards to stage data, or if there's a reducing trend. And also host exponent is a very popular trend analysis that is used in hydrology. The idea is just to test if a system can remember its memory. That's just the idea of host exponent, if it depends on the past event or it does not depend on past events. So exceedance metrics or drought characteristics was also itemized, and just like I said, relative elevation model were all used to look at hydrological drought and floodplain disconnectivity. So how did we identify low flow conditions or low flow thresholds? The USGS, through Light et al. 2013, has performed an intensive research within the Apalachicola River. They were able to bring out different low flow thresholds. The first one was designated in 2006 when a large amount of freshwater mussels died off at Swift Slough. The idea is that immediately the water level was at 141.5 and below it, all the freshwater mussels just died off. So this became an ecological threshold as the first threshold to use to be able to determine the disconnectivity. So the second threshold is impassable streams, which is 169.8. So this impassable stream is actually talking about when over 85% of non-tidal floodplain streams and sloughs become inaccessible. Nobody can go there. Farmers can't go there. You cannot use your small boat to pass it because the water level is really, really low. The other threshold is low flow operations, which is 22.64. So minimum flow required for fish reproduction and access to off-channel and floodplain spawning. So any water level that is at this level or below, fishes can no longer go to the floodplain to spawn. So this became the thresholds that we used to analyze. So they are actually ecological thresholds. So we took this threshold and their corresponding stage height, okay? Then we created what is called detrended stage elevation. So detrended stage elevation is to take this stage height, take the digital elevation model I created in the first paper, then say the DEM minus the stage gives us detrended stage elevation. So to create a relative surface water model, which is also called REM, we said the DEM, original DEM, minus the detrended stage elevation. So this actually gave us the depth of water across the entire floodplain. So it was easy to be able to say, oh, anywhere where there is negative sign simply means it is disconnected. All right, so if it's positive, so anything below zero is disconnected. Anything above 0 is connected. So the relative elevation model was able to give us that. Very simple. And of course, not just only REM, we also looked at drought characteristics, frequency, which represent the number of times the flow drops below any of those thresholds. And also duration, total number of days the flow remains below that threshold, our duration. Also the magnitude. What is the magnitude? How big is the drought? Okay? So this is the first result, which is Mankenda, simply saying the annual threshold, where you see that even the stage height consistently has been reducing apart from the first time of pre-dam period. Now, if you remember the first paper I presented, that water level has been reducing because of degradation. So over time, you see that the level of water has been reducing in the channel over a long period of time. Now, when we are talking about Hauss exponent, when you say 0.5, you say it is non-persistent. That means the trend doesn't, depend on the mean. When you say if it is greater than 0.5, you say it's consistent with the mean. That means it depends on the mean. But if it is less than 0.5, it is anti-persistent. What it simply means is that anytime there is a high value of stage height, the following value becomes low. That's what it means. So it means that, and also vice versa. So any high value gotten from stage height within the series, the next value is going to low. Simply means that the amount of stage data is decreasing consistently across the entirety of the floodplain. So when you look at the drought characteristics, including frequency, duration, and magnitude, so you see that it has been increasing post-dam period. So remember that the dam was constructed, started construction 1954. It was opened in 1957. So imagine before that and after that. So you can see the magnitude and the duration of this event, drought event, using those low thresholds. They are actually increasing as a result of what is happening in the river. Of course, all those human activities. Also, we try to use a monthly, because what we used before were fixed threshold of certain numbers. But we try to use a variable threshold, 20th percentile, meaning that anytime that the value or the discharge goes below the 20th percentile every month, we regard it as hydrological drought. So you also look at, of course, the Blountstown do not really have discharge data, from the 1920s, or except from 1958. So when you look at it, you realize that even closer to the more recent time, the duration and magnitude and frequency of these hydrological drought events are actually increasing. Now, let's look at the eco-surplus and eco-deficit, looking at how then do we use stage to explain what is going on within that channel. So remember that I said eco-surplus and eco-deficit are actually hydroecological terms that try to look at changes in flow regime using flow duration curves. So after the event, which is from 1954 when the dam started construction, now you see that there is an eco-deficit after it, meaning that water flow is actually reducing, all right, after it. But I mean, 5 to 15% of it shows, eco-surplus. But when you look at this data, you see how close discharge is showing what is going on within that river channel. It is not showing it markedly or substantially showing that something is going on. But when you look at discharge data doing the same thing, so you see how discharge data show that there is a great difference with regards to what happened in pre-dam and post-dam period. So if you teleport the eco-deficit and eco-surplus into this graph, you better explain that there is a huge difference between what is actually going on using the stage data to try to interpret the changes in inundation within the river channel and also the floodplain. When you look at connectivity, thinking about our HEC-RAS model and look at how the different water level actually affect connectivity of the channel. So you see at 19.3, which is at 1500 cubic meter per second, this is pre-dam and this is post-dam. So you see there is the differences in stage height. And you also see not just differences in stage height, also in the inundation, reducing connectivity between the main channel and the floodplain. Cut across all other flows, and each flow, the same flow, equal flow, has different stage height. So you see, even though when the flow is similar before the dam was constructed, the stage height has actually changed, signifying that the water level is actually dropping as a result of what the incision caused by the dam. Now again, another explanation is looking at the depth of the tributaries when we pick the relative elevation model. So this is Mosquito Creek. So I try to pick a point where the mouth of that tributary is feeding the main channel to see what happened across different thresholds. So for the 170 discharge, so you see for Mosquito Creek, here the blue says pre-dam, while the orange is post-dam. Anything below 0 signifies disconnectivity. So you see how much of the channel is disconnected, especially. Remember we talked about that the frequency, duration, and magnitude of all the hydrological drought is actually increasing, all right, across different flow period. So you see how they are, even when you look at all the different thresholds, this connectivity is actually increasing for all of the tributaries when you compare pre-dam and post-dam period. But when the channel has a lot of water, it kind of reduces. All right, so when there is low flow, that's when you have more of this impact. In other words, it means that low flow condition actually shows more impact of human activities on the channel as opposed to when the river has a lot of water. Also, this is just a very big map to show what is actually going on within the entirety of the floodplain. So when you look at it, the yellow and the brown showing moderately disconnected and highly disconnected floodplain. So when you look across, comparing the pre-dam and post-dam period, you will see that the yellow and the brown is increasing, signifying that there is more disconnectivity within the floodplain across the entirety of the channel and the floodplain, and also between the post-dam and pre-dam period. So what is the take-home message? That the frequency, duration, and magnitude of low flow conditions has increased significantly post-dam period. So stage markedly show hydrological drought because of degradation. Relative elevation model actually shows disconnectivity of the tributaries with the floodplain. Now I was saying in the beginning, what is more? So, of course, we've looked at different, I said that this work is actually a very huge work. And part of the things that we did was to try to say, oh, we have discovered that this and this are happening to the channel. That how do we help the river to recover? Since dredging stopped in 2002 and the river is undergoing passive recovery, how then do we help the river to recover? So we started going back and we started planting willows. We started taking GPS position and start planting willows across the entirety of the floodplain. But this was not very successful. Because when there is high flow, what happens is that most of the willows that we planted are washed back into, but in some cases, you know, here is me trying to take a GPS position of one of the willows. In some cases, we had some success, and we have learned a lot. Of course, we didn't get a lot of success in trying to plant trees across the floodplain to help the river to recover. But in some cases, we had some success, and we have learned from it. You have a question?
What made you choose willows versus like cypress or
Yes, yes. I've forgotten the other plant that we tried. We had two that we tried, but we realized that this was more resilient. So when we planted all of them, they all died off, but this survived.
There's also a pretty standard manual that the Army Corps requires that have things like willow for stream bank stabilization and connectivity projects.
Yes.
Which is woefully outdated.
Yeah.
Not recommended in most real.
All right, I think this will end it. Thank you so much for listening. If you have any question, you can ask. Thank you.